This is my second video lab report for Physics 2211. This is Lab 2, in which I observed an object falling from rest. The system I chose to create was dropping a soccer ball from a height of about 2 meters. So here is the tracker video that I recorded and placed the mass points on. So due to the nature of the system, the initial velocity of the ball was 0 meters per second and accelerated at a rate of negative 9.8 meters per second squared in the negative y direction due to the gravitational force of the Earth. And this negative velocity, or this negative acceleration, was countered by the effect of turbulent drag. Now, turbulent drag is equal to the square of the speed of the ball multiplied by an experimental drag constant that, in this case, is simplified for the purpose of the lab, but really encompasses a lot more factors that we're just not going to get into. Now, as the drag is a function of speed, it's also a function of time, so no singular true acceleration can be stated as a single number if you try and combine the drag and the gravitational force. So after completing the work in Tracker, I made a computational model in Python that involved only gravity but no drag force. So here's the file. You can see here's the main loop that does the actual projection of the velocity, position, and dealing with net force. I made a couple edits in terms of delta t and the mass of the ball, and then let's run it. So here you can see the ball drops straight down. You have your yellow arrow denoting the force vector for gravity, and then now we're going to move on to adding drag. So here is the next computational model that actually incorporates drag into the model to make it more realistic. So it's all the same as the previous one, except for right here I added a drag constant of 0.21896, which is multiplied by the absolute value of the velocity, the speed, which is then squared. And that will counteract the force of gravity to slow it down and create a less drastic drop. So now we're going to run the program. And we can see here that both these programs are running at the same rate. You can see here that the ball drops slower. It has a slower velocity overall. It also travels a shorter distance. Instead of going over 3 meters, it goes a little over 2. Now in this model, the yellow arrow also represents the force of gravity, but this also has a blue arrow that denotes the force due to drag. And so you can see at the end here, those arrows are roughly equivalent, which means that the ball might have reached terminal velocity. So here's a graph with all of the data from the observed system and both computational models together to show the model drop with and without the effect of drag compared to the observed data. Now you can see here that the model with drag fits a lot better because of the drag coefficient that was carefully selected to create a best fit, while the model without drag accelerates much faster. According to Newton's second law, the net force on a system is the sum of all the pushes and pulls on the system. This is why the first computational model without drag was vastly inaccurate, because it did not account for the force of drag, which serves to counteract the force of gravity to a certain extent. Now let's talk about terminal velocity. Velocity here is the slope of the graph, because this is a position versus time graph. Now, terminal velocity is impossible in the first computational model without drag because there is no opposing force to halt the acceleration due to gravity. However, with drag force as shown in the second computational model, there is terminal velocity where acceleration halts and the slope of the position versus time graph becomes linear. This is because at some point in time, the drag force grows to a point at which it is equal to the gravitational force, yielding a net force of 0 at that point and onwards. The net force stays at 0 because the gravity does not vary, obviously, and the speed will remain constant due to the net force of 0. And the drag force is a function of speed, therefore that will stay the same. On the other hand, what if the ball is thrown down and not dropped? Well, it would still achieve the same terminal velocity because at the same speed for both systems will the drag force negate gravitational force and yield constant velocity. The difference is simply that the ball thrown will achieve terminal velocity in a shorter period of time.